Moments. Here we have two people of equal weight on a seesaw. They're both the same distance from the pivot, the centre point about which the beam turns, and so the seesaw is balanced. Here we have another seesaw. The person on the left is now much heavier than the person on the right, but they're sitting closer to the pivot point, and so the seesaw again is balanced. This is as the moments are balanced, moments or turning effects. The moment is equal to the force, in this case the weight of the person, multiplied by the perpendicular distance from the pivot. When in equilibrium, the sum of the clockwise moments, in this case caused by this person turning the beam clockwise, is equal to the sum of the anti-clockwise moments caused by this person. That is known as the principle of moments. The weight here, multiplied by the perpendicular distance d1, will equal the weight here multiplied by this distance, giving us this expression. For perpendicular distance, here we have a lever which is at an angle from the pivot, and the force is acting vertically down. What we mean by the perpendicular distance is not the length of the beam here, but the distance which is acting at 90 degrees to the force, in this case this distance. At GCSE, you'll be given the perpendicular distance. Here we have a seesaw with one person on the left and two on the right. In this case, the sum of the clockwise moments, which is the weight of this person multiplied by their distance, plus the weight of this person multiplied by their distance, the expression here, is equal to the sum of the anti-clockwise moments, the weight of this person multiplied by this distance, given by the expression here. We have an example. A 300 Newton child sits 1.6 meters from the pivot, balancing another child 1.8 meters from the pivot. What is the weight of the second child? In general, problems will give you 3 of the 4 quantities of the forces and the distances, and you will be asked to work out the fourth. So, from this expression, we know that the weight of the second child is given by this expression. All we need to do is put in the values, making sure, as always, that we convert to SI units, but in this case we're given weight in newtons and distance in meters, so no problem. This gives a weight of 267 newtons. The 300 Newton child now moves out to sit 2 meters from the pivot, with the lighter child staying still, but joined by a friend of weight 180 newtons. Where must the friend sit if the seesaw is to remain balanced? Well, again, using this expression, we've got d3 now, as we have the weight of the first child multiplied by their distance is equal to the moment of the second child plus the moment of the third child. Putting in the values, we get a distance of 0.66 meters. We can use the principle of moments to find the weight of a meter rule. Find the point about which the rule will balance. This is called the centre of mass, and is the point about which we can assume all the weight of the ruler acts. If the rule is uniform, this will be at the centre. Now we use a known weight to balance the ruler off centre. So the pivot is now along to the left side of the ruler, and we have some weights here which are balancing the ruler. This will give the expression of the weight of the weights, and that is distance of weights from the pivot. The weight of the ruler we can assume acts at the centre of mass, in this case the centre of the ruler, and I've called that weight R for weight of ruler, and that is distance ruler. We get this expression. We want to find the weight of the ruler. All we need to do is put in the values. We could take several readings and find the mean.